Well, happy off-campus learning day. My name is Mr. Royce. We're going to get ready to turn in the homework that's due on Monday. I'll be your video instructor for today. We have a video student here who's going to be watching to make sure that if there's any questions and that those get taken care of right here on the video. So here we go. The homework that's due on Monday for Algebra 2. There's three things you have to have done by Monday. First of all, homework 2.4. I'm going to start today by teaching homework 2.4, and that is due online submission by class time on Monday. The other thing that's due Monday is homework 2.5. I taught that on block day. Homework 2.5 is an online submission also, and that's due by class time on Monday. The third thing that's due class time Monday is to complete the notes for lesson 2.6a. It's not homework, it's just notes. And I'll be leading you through the notes here in this video. So as long as you can bring the paper that you use to take notes on this video, just bring the paper notes with you, which I handed out on block day. Bring those on Monday, turn them in, and you'll be good to go with all three of these. So we're going to begin with homework 2.4. And here's what we're going to do with homework 2.4. Instead of using the paper notes to do problems, the homework is problems 1 through 7. We're going to do problems 2, 3, and 4 on the video. We're going to be doing the homework problems during the video, so that for homework, all you're going to have to turn in is problem 1, and then problems 2, 3, and 4, which will be your notes basically from this video. We'll do those here. And then, so you'll do 1, 2, 3, and 4 is in the video, 5, 6, and 7. So the only ones you'll have to do on your own from assignment 2.4 will be problems 1, 5, 6, and 7. So by doing homework problems 2, 3, and 4 on the video, those will serve as examples of what you need to do. So let's jump right in to lesson 2.4. I do have a warm-up question for you here. This is a problem that was on the PSAT last year. A lot of Wheaton Academy students missed this one. I'm going to read the problem. It's multiple choice, and then I'd like you to pause the video and think about it and pick either A, B, C, D as your answer. In case you can't read that, it says, this was problem 21 from last year's PSAT. It said, as part of a promotion, a radio show host gave away 3 pairs of tickets each day until all the tickets were gone. The relationship between the number of pairs of tickets, Y, that remained at the end of each day and the number of days, X, since the promotion began, can be modeled by the equation. And by the way, model is the key word for homework 2.4. We're learning how to understand mathematical models. By the equation Y equals 60 minus 3X. If the graph of this equation is sketched on the xy plane, what will the x-intercept of the graph represent? You have 4 options here. Just one number. It's mostly words. This is mostly a verbal problem. A, the x-intercept represents the number of pairs of tickets that were given away each day. B, the number of pairs of tickets at the start of the promotion. C, the number of days it took to give away 3 pairs of tickets. And D is the 4th option, the number of days it took to give away all the pairs of tickets. So go ahead and pause the video, think about it, and pick one of those 4 answers. Welcome back. Okay, I'd like to show you how I would approach this problem. First of all, using what we learned about sketching the graphs of lines that are in the form y equals b plus mx, notice on the PSAT, they did not use mx plus b form. They used b plus mx form, where the intercept is 60 and the slope is -3/1. So we can think of the line y equals 60 plus a rise of -3, a run of 1 times x. So we start out, we begin the problem at 60. 60 what? Well, it says y is the number of pairs of tickets. So on day 0, if x is the number of days and y is the number of tickets, that means we begin this model with 60. We start out with 60 pairs of tickets. We go down 3 over 1. So we go down 3, right 1, and with a negative slope, we are going to hit the x-axis eventually. So they're not asking us to find that number. They're just asking, what does this x-intercept represent? And when I look at what x means, there is meaning attached to x. It's x represents the number of days since the promotion began. So let's find out what this is. Let's solve for what x is, even though they're not asking us to do it. The x-intercept corresponds to y equals 0. So we get 0 equals 60 minus 3x. When you add 3x to both sides and divide by 3, you get 20. So even though they're not asking us for the x-intercept, we do know what it is. It's 20. And what that represents is that it took 20 days for the number of pairs of tickets to dwindle to 0. So let's see which one that would be. The number of days it took to give away all the pairs of tickets. There it is. Letter D was the correct answer. Very few students got that one correct. So probably because it required you to put the V in vegan tomorrow. You had to understand verbally and in the context of the real world what these linear functions are all about. And that's exactly what we're going to be doing. That's exactly the lesson in assignment 2.4. Now, if you don't have the book in front of you, I do have the problems here. Problem 2 from homework 2.4 is, and you'll see this in your textbook if you look this up in the syllabus, find out what page number it is, but problem 2 says that a pump removes 1,000 gallons of water from a pool at a constant rate. So instead of starting out with 60 pairs of tickets, we are starting out with 1,000 gallons of water in the pool. And instead of giving away 3 pairs a day, which by the way, they could have asked all sorts of other questions. On that PSAT problem, they could have asked what the y-intercept represents, 60. If they had asked that, we would have said, well, that's where we start out. Instead of starting out at 1,000 gallons of water, it's like they started out with 60 pairs of tickets. They could have asked you what the slope represents, in which case you could have said, it's the number of tickets that the number of pairs of tickets that we give away each day. You are expected to have a real world understanding of every part of this linear model. And so let's take a look at this situation. We're expected to write a model. We have to be creative. We're going to write an equation to find the amount of water in the pool after t minutes. So let's finish reading the givens. A pump is taking out 1,000 gallons of water from a pool at a constant rate. So instead of giving tickets away at 3 pairs of tickets per day, we are pumping water out of the pool at 50 gallons per minute. So they're giving us a slope. They're giving us a rate of change. So since writing linear models and interpreting them is a really tough part of the PSAT. The SAT is very verbal in nature. We're going to make sure that we understand verbally what's going on. Instead of just focusing on how to do the problem, let's focus on really understanding it. And the first step in really understanding a problem in a verbal environment is to write what's called a verbal model. Please write sideways like this so that we can organize our paper in such a way that everything will actually fit. So here's the verbal model. It's inspired by the idea of a linear model, which starts out with what it is we're trying to predict. I mean, I'll be honest with you, I do have y equals b plus mx in my mind as I create this verbal model. So my verbal model is going to have 4 boxes with words inside of all 4 boxes. So notice that in this case, instead of using y, well, actually we are using y, but instead of x, we're using, for the input, we're using t. So y is the amount of water in the pool after t minutes. So please write the words amount of water in the pool after t minutes. And put a box around that. Now, for my use of space, I'm actually going to shrink that down a little bit so that I can present all this together, but we're trying to create a model. It says write an equation to find the amount of water in the pool after t minutes. So that's my first box. That's y. Now, next, I'm going to write the equal sign, and b in the PSAT, that was where we started out. We started out with 60 pairs of tickets. B tells you where you're starting. Where does the problem begin? So in this case, instead of the initial number of tickets, here I'm drawing a box, and now I'm going to draw words inside the box. That's a little bit risky, because what if the words won't fit in the box? So usually I would want to write the words first, but this is the amount of water in the pool at time 0. So please write the words amount of water, I'll write H2O, in pool at t equals 0 minutes. At t equals 0 minutes. Okay, that's where we begin. So to find the amount of water in the pool after t minutes, I have to start by thinking about, well, how much water do we have at the beginning? What's the initial amount? Plus, and now the slope, that's your rise over run when you're doing just pure math. But in the real world, the slope is the rate of change in the water per minute. So let's write that verbally. Words first, and then the box. Rate at which the number of gallons changes. Slope is a rate. So please write the words rate at which the number of gallons changes. A slope is always a rate of change when you create a real world model. I write the words first, I'm going to write a box around it, and I'm going to size it so it fits on our screen. So that kind of takes care of the slope. Now the input. The input is not x. In this case, it's t, which is the number of minutes the pump has been operating. So instead of multiplying by the number of days that the ticket giveaway promotion has been operating, here we're going to multiply by the number of, words first, the number of minutes pump has been operating. The number of minutes pump has been, we'll say it's been on. Okay? So, 4 boxes. Linear models tend, in the real world, which is where it gets tough for Wheaton Academy students on the PSAT and on the SAT, by writing out these 4 boxes with words in every box, that shows that you're engaging in the ideas that underlie the equation. In the real world, equations are based on ideas, and the ideas should be true. To find out if these ideas make sense internally, we're going to switch to light blue, and this is how the homework solutions are set up. We're going to check the units. UNITS. Let's just examine the units. The amount of water in the pool after t minutes, so that's going to be measured in gallons. So under this first box, just write GAL. We'll measure water in gallons. The amount of water in the pool at the beginning will be measured in gallons. The rate at which the number of gallons changes, that's going to be measured in, you can see it right here, it's in gallons per minute. So write a fraction with gallons in the numerator and minutes in the denominator. and minutes are measured in minutes. The reason we're writing out the unit model, which doesn't take very much, I'm going to shrink this down, is to see if it makes sense. You see, if you take gallons per minute times the number of minutes, this is like minutes over 1, the minutes cancel. So you end up with this idea of gallons equals gallons plus gallons, which makes sense. If you ended up with a model where the unit analysis said something like gallons equals feet plus years, then that's a signal that your model is out of touch with reality, because it doesn't make any sense to say gallons can be found by taking the number of feet plus the number of years. So make sure that the units make sense. That'll give you confirmation that your idea is correct. So after the verbal model and its units are done, next we move to the algebraic model. Okay, so word problems are tough. That means we need to put in more effort to start getting these right. Algebraic model. This is a high stakes issue. SAT is a high stakes test. So I know it may seem like this is taking a long time to go through it, but when you're in a test situation, if you're used to doing verbal modeling, it'll go through your mind pretty quickly. It just takes longer to explain it. So for the algebraic model, for each of the 4 boxes, we need an algebraic symbol, either a number or a letter, to represent each box. For the amount of water in the pool, they've asked us to use Y to represent that. What meaning is going to be attached to the initial amount? Well, they told us the initial amount was 1,000. What's the rate of change? Since we're pumping it, since you see the word remove there, that word remove is a verbal negative sign. So that means that the slope is negative 50 gallons per minute times the number of minutes. They've asked us to use the letter T to represent the number of minutes. So this is your algebraic model. It's based on an idea that is true as indicated by the unit analysis. So after the algebraic model is done, and I'm going to shrink that up a little bit, that says algebraic model. Next, we can answer the question. Part A asks us for the equation to find the amount of water in the pool after T minutes. So the answer to part A is our algebraic model. It is Y equals 1,000 minus 50T. Now, some students are going to be like, well, I knew that without doing any work. Well, right, just get in the habit of writing a verbal model. It will develop your ability to connect mathematics to the real world, which is currently a huge weakness for students on average. The second part says, graph the equation and interpret the intercepts, just like they asked on the PSAT. This is an example which was basically exactly like that problem with handing away pairs of tickets on the PSAT. So let's go ahead and sketch the graph and interpret the T and Y intercepts. So they're asking for words. They want us to write a little essay explaining the meaning of the intercepts. So here we go. The first part of the answer to part B, which is to sketch the graph, means that we don't have X and Y as our labels. We have T on the horizontal axis and Y as the label on the vertical axis. And since the intercept is 1,000, we start out not at 60 pairs of tickets, but we start out at 1,000 gallons of water. And because the slope is negative, we're going down 50 gallons every minute, down 50 every minute. We know the slope is going to go down in such a way that it eventually hits the t-axis. So they're asking us to write a little paragraph explaining what the y-intercept means, and write another little paragraph to explain what the t-intercept means. So I'm going to type these for you so that it's really super clear. And there we go. That went away for a second. And we can do, I think blue usually shows it pretty well. I want to see if I can make it bigger writing. Let's go up to 22 point. So I want to explain, or I want to type in the meaning of the y-intercept. So here's how we could type it. We could say that the y-intercept of 1,000 indicates the number of gallons of water in the pool before the pumping began. Okay, it's the number of gallons of water in the pool before the pumping began. So it's the initial, or you could say it's the initial amount of water before the pump began. So that's the interpretation of the y-intercept. Now, if you want, I would recommend pausing the video, write out what you think an interpretation of the t-intercept would be. Just pause it, and then when you have it written down, unpause to see if it matches my interpretation. So pause the video and write it out on your own. Okay, welcome back. So here's a good interpretation of the t-intercept of the video, the t-intercept of the graph. I'm going to write it like this. The t-intercept of 20 indicates the number of minutes required to pump all 1,000 gallons out of the pool. So instead of the number of days it takes to give away all 60 pairs of tickets, this time the t-intercept represents a similar idea. It's the t-intercept 20 indicates the number of minutes required to pump all 1,000 gallons out of the pool. Now, graph the equation and interpret the t and the y-intercepts. They didn't ask you to find the t-intercept, but they did ask you to sketch the graph, so we should put a number here. And to find that number, we do have to do a little bit of algebra. Let's take our model, which is y equals 1,000 minus 50t. And to really complete our graph, let's find out how to get that 20, because here's a 20 here, but I hadn't yet solved the equation. So let's do the work. If you take this as your original equation, let's put a 0 substituted in for y, because when all 1,000 gallons are out of the pool, that means y will have a value of 0. And that equation becomes 0 equals 1,000 minus 50t. We're going to add 50t to both sides of the equation to get 50t equals 1,000. And of course, divide both sides by 50 to get the final answer of 20. So I've gotten a little bit ahead of myself there in terms of that number 20. But here's how you would do the algebra to solve for 20, and then here's the interpretation. So that's problem 2. My aim here in lesson 2.4 is to actually do homework problems 2, 3, and 4. Those will serve as examples for the other problems on the homework. So, problem 3 from homework 2.4, as you can see in your textbook, and I'll read it here in case that's too small for you to read. Problem 3 says a tree that's 5 feet tall grows an average of 8 inches per year. This is going to be an issue with units because we're mixing feet with inches. So that's going to be a high stakes issue when we do our unit analysis. Write and graph an equation to model the tree's height after X years. That's all they're asking for. Just write the equation and then sketch the graph. So we need a verbal model again. And since verbal models are the sorts of things that algebra students sometimes wrestle with because they're verbal. It's words inside boxes. But this is the most important part of doing high stakes tests that are verbal in nature. I would like you to pause the video and try to write out 4 boxes with words in each box. It will be, the skeleton of it will be 4 boxes where it's big box equals box plus box times box. It's inspired by y equals mx plus b. So here's my challenge to you. Pause the video and see if you can fill in the words for all 4 boxes in the verbal model. Let's give that a go, and then we'll take a look at it together. Okay, welcome back. I think one good way to fill in the words for the verbal model is, there's some clues right here. To model the tree's height after X years. So they want the height to be the output of the function. We'll put the input of the function, which is the number of years, over here. So we can say the height of the tree after X years. This is the first box. Get us in blue. Keep the color coding consistent. Height of the tree after X years. Okay, that's the output of the function. Make that a little bit smaller now that we talked about it. And just like on all the problems so far, there's been this idea that the model starts out at the beginning of the ticket giveaway, at the beginning of pumping out the water from the pool. Here we're at the beginning of the tree growing in inches per year. The beginning is 5 feet. So we're going to call that the initial, or you could say the beginning height of the tree. This is initial height of the tree. Okay, so now that we've written that, we can make it a little bit smaller, put it into place. And now here's the slope. This is the rate of change. So we can call that the constant rate of change in tree height per year. Constant rate of change in tree height, or just height, per year. Per YR per year. That's the slope. And then this is going to be the number of years. The number of years that the tree is growing. So only 3 words, number of years. So we're going to make an M like this today. Next, I'd like you to try the unit analysis on your own. Please press pause and try to fill in the unit analysis, and then come back and we'll take a look at it together. Hey, welcome back. The unit analysis, the height of the tree after X years, they didn't tell us whether they want inches or feet. I think it's easier to work in inches. So we're going to measure the height of the tree in inches, IN for inches. So the initial height of the tree should be measured in inches, even though it's given in feet. When it comes to filling in the initial height of the tree, we're going to have to commit to inches. The reason I went with inches is because the slope is given in units of inches per year, and years are measured in years. So the unit analysis makes sense. Years divided by years cancels. We get inches equals inches plus inches. That makes a lot of sense. We don't want to have something like where feet equals inches. That would not be a good model. So now let's write the algebraic model. The color I've been using for algebraic models is green. So this is the algebraic model. And height of the tree, they want us to use H for that. The initial height is given as 5 feet, but I need it in inches. So 5 times 12 is 60, so I'm going to have to use 60 for the initial height of the tree since we're in inches. We're growing at 8 inches per year times the number of years. They've asked us to use X for the number of years. Therefore, when they say write an equation and graph it, the equation is H equals 60 plus 8X. Let's red box that to indicate it's a final answer. They've also asked us to sketch the graph. They have not asked us to interpret the graph. But please do not reflexively or in knee-jerk fashion just write a y up here. It's not a y-axis, it's an h-axis. Here's the x-axis. the intercept is 60, and we're going up 8 inches over here, so it's going to have a positive slope. How much do we need for a full graph? Well, we should put at least one other point on it. Maybe we should go 1 year into the future. Golf ball 1 goes up to a height of 68. So we got 1, 68. That's a graph. And if someone did ask you to find the intercept, you could put it, if you want to find out, you know, what was the value of X, what was the number of inches per year. So how many years, if you wanted to know how many years ago the tree was at 0 inches, assuming it was a constant rate of growth the whole time, which it may not have been, but you would put a 0 in for H. If you solve for X, you would get negative 7.5, which indicates that the tree may have been planted 7.5 years ago, but that prediction may not be accurate because they didn't say that from the time it was planted that it was growing. But they did say from the time it's 5 feet tall, it's growing at 8 inches per year. One more. So this last one that we're going to look at together, before I turn you loose to do the rest of homework 4 on your own, is problem 4. For each situation, it says find a linear model. That word model was used on the PSAT, and use it to make a prediction. Okay, so this time we're going to use the model to go one step further. We're going to make a prediction with the model. So the problem reads, there are 2 leaves along 3 inches of an ivy vine. There are 2 leaves along 3 inches of an ivy vine. And there are 14 leaves along 15 inches. So there's this vine. Just to draw a little picture of this, sometimes it helps you. So there's this vine, and maybe they're measuring how long it is, maybe from like the 5th inch to inch 7, so that's 2 inches. Maybe they noticed that there are 2 leaves along, oh, it says along 3 inches. So I'm going to change the 7, 2, and 8. So the 3 inches from 5 to 8, someone counted 2 leaves. And then they took a 15-inch segment and they counted 14 leaves. How many leaves are there along 6 inches of vine? Well, it looks like the longer the vine, the more the number of inches. Let's actually use a 4-box verbal model to get a handle on this idea. And yeah, I can see in this problem it'd be really tempting to oversimplify it and just set up a proportion where you have a fraction equal to a fraction. But that would assume that when the vine is 0 inches, that it has 0 leaves, which seems reasonable, but let's look at the power of verbal modeling as we try to fill in all 4 boxes. So here we go. If you want to try it, press pause and try it on your own. Here we go. How many leaves are there is what we're trying to predict. So number of leaves along X inches of vine is the first box. It's the output. Our model is going to predict the number of leaves along X inches of vine. We're not trying to predict the number of pairs of tickets at the radio station after X days or the number of gallons in the pool after T minutes. We're trying to predict the number of leaves along the vine that is X inches long. So that's the Y in Y equals MX plus B. Next, we need the starting amount, the number of leaves along 0 inches of vine. And I know that seems like that would have to be 0, but our model might say otherwise. So this is a real stretch to think that this number might be something other than 0, but I'll just give you a heads up. It is a number other than 0. It's not going to end up being 0. So trust me on this one. Number of leaves along 0 inches of vine. Turns out our model is not going to say that's a number 0, even though it seems like it should be. Now we need the rate of change. We need the constant rate of change in number of leaves per additional inch. So we're going to call this the constant rate of change in the number of leaves per additional inch of vine, per additional inch. Okay, so that's a lot of words, but that's the idea. It's a constant rate of change in the number of leaves per additional inch. I'm going to shrink this up a little bit. And then, of course, the length of the vine is the last box. It's not the number of days that the promotion is going. It's not the number of hours that the pump is running. It's the length of the vine, or the number of inches of the vine. We'll call it length of the vine. Let's go through and do our unit analysis. Number of leaves. They haven't given us letters for this, but we'll, units, we're doing light blue. But the number of leaves will be measured in leaves. And L-E-A-V-E-S. Constant rate of change, that's going to be in, it should be plus here. So this will be leaves per inch. How many leaves per inch? And then the length of the vine will be in inches. So inches cancel, we have leaves equals leaves plus leaves, that makes sense. So now, as we get a verbal model for the algebra, as we use our verbal model to get an algebraic model, we're going to have more letters and fewer numbers than we're accustomed to having. So please label this your verbal model. Okay, leaves, let's use the letter L. The initial number of leaves, we don't know that. They didn't tell us. We're going to have to solve for it. So let's call that B. Kind of in the spirit of y equals B plus mx. We don't know yet what m is, the slope. So we're just going to use m for that. We can use x for the number of inches. So 4 different letters. We're going to have to calculate the slope. And that's a new step that we did not have to do on the previous problem. But we're going to use this information they gave us. It's like they gave us 2 points on the line. When x is 3, L is 2, I just want to summarize what they gave us here in a table. And you're going to have to do this on several of the other problems. This is a section called Calculation of Slope. C-A-L-C, calculation of S-L-O-P-E. We have to calculate the slope. And that's something that we learned how to do in this unit. In fact, what I can do is I can set this up as X number of inches, L number of leaves. So they told us at the beginning when there's 3 inches on the vine, there's 2 leaves. So 3 inches, a vine has 2 leaves. And when there's 15 inches, there's 14 leaves. So 15 inches, 14 leaves. So what we're going to do, instead of y2 minus y1, we're going to say that the slope is L2 minus L1 over x2 minus x1. Making the substitutions, we get 14 minus 2 over 15 minus 3. So I'm looking at 12, came out to be, that's nice. They gave us a slope of 1. So we're doing the calculation of the slope, but we also have to do a calculation of, in fact, I'm just going to make this magenta, the M for the slope. I'm going to do the color coding with this work. And then we're going to have to calculate the intercept also. I know it's easy to assume it's going to be 0, but it's not in this case. So we're going to call this calculation of B. C-A-L-C, calculation of B. And that work's going to be right over here. I'm going to use point slope form for the calculation of B. And the L, number of leaves. I used L for leaves. I could have used N, and I was looking at the online solutions. On the online solutions, I use capital N for the number of leaves, but I'm using L in this example, so that's fine, we can do that. So instead of Y minus Y1, it's L minus L1 equals M times X minus X1. It doesn't matter which of these 2 points I use. I may as well just use the point 3, 2. So it's going to be L minus 2 equals the slope, which is 1, times X minus 3. And I'm just going to put this into a form in which I can see what the intercept is. I'm going to add 2 to both sides to get L equals X minus 3 plus 2. So L equals X minus 1. There it is. Y equals MX plus B. I just discovered that B is -1. So in my quest to calculate the value of B, I used point slope form and compared the equation that showed up to Y equals MX plus B form. So here's what my thinking was. Y equals MX plus B. Instead of Y, we're using L. M is 1. We knew that. We knew the slope was 1 from this work over here. X, and then the -1 lines up with B. That's the basis on which I conclude that B is -1. So that means we finally have a model. They said how many leaves are on the line. So we have our model. The model had 4 letters in it, but now we have M is 1, B is -1. So now we know what the model is for L as a function of X. So let's write the algebraic model in green as L equals B is now known to be -1 plus X. So this is the model that we use to make predictions. They want us to predict the number of leaves along 6 inches of vine. So we can think of that in function notation. It's like, what's L of 6? What's the height of golf ball 6? It's going to be -1 plus 6, 5. And since it's a word problem, we answer our questions in verbal form, just like the SAT wants us to answer questions in verbal form. So what we say is that when there are 6 inches of vine, 6 inches of vine, the model predicts we will see 5 leaves. We don't know for sure that's what it's going to be. This is just what the model predicts will happen. The model predicts we will see 5 leaves. Okay, so that's it. That completes homework 2.4's lesson. You can do the other ones on your own. Now, the other part of this video is to look at 2.6a. And the notes that you take on 2.6a are not associated with homework. It's just a matter of turning in these notes that you take. So I gave you the paper for this. If you don't have the paper, you can always download it. The notes are online. And it'd be a good idea to have a calculator out for this. I've got my calculator out and ready to go. I hope that you have your viewing window set from -6 to 6 on both the X and the Y axis, just like we did in class. So here we go. From 2.6a, they ask you to think back to section 2.5 in the homework there. They had 2 graphs, and this, we're going to show you a folding technique of how to get that V-shaped absolute value graph without using the X-child and Y-child equations. And it works in a very small fraction of these cases, but it is kind of interesting to see it in this small set of problems where this folding technique works. If you were just going to sketch the line without the absolute value, the intercept would be -1, 2, 3, 4 with a slope of up 2 over 1. Up 2 over 1. So here's the graph of y equals 2x minus 4 without the absolute values. Now, if you sketch the graph with the absolute values, and the way that we learned how to do that in class was to say, well, let's take the parent function. The parent function is the absolute value of x, which has 3 key points, x parent, y parent. Golf balls -1, 0, and 1 go to altitudes of 1, 0, and 1. And if you were to look at the linear transformations that occur, we learned how to take, first of all, there's nothing happening to the parent y values, but to the parent x values, instead of multiply by 2, subtract 4, we're adding 4 and dividing by 2. So if you wanted to find 3 points on the graph of the child function, you would take the triplet of y values. They are unchanged. Y child, y parent, they're equal to each other. But you would, I want to focus in on the orange here, the triplet of orange values can be found by taking the orange movie and watching it backwards. Instead of multiply by 2, subtract 4, we're going to add 4 and divide by 2. So let's follow that plan. -1 plus 4 is 3, divided by 2 is 3/2. 0 plus 4 is 4, divided by 2 is 2. Make this a little more visible. This is 3/2, or 1.5. Now let's try the third number. 1 plus 4 is 5, divided by 2 is 5/2. So that's 1.5 comma 1, 2 comma 0, and 2.5 comma 1. So you got a V-shaped graph here. Now, the purpose of comparing these side by side is to say, well, look at this. Whenever the vertex is on the x-axis, which is not very often, but when it is, you see a special relationship here. You can see that the absolute value bars have the effect of taking any golf balls that are below ground, basically any outputs of the function that are negative, the absolute value function will flip those up and make them positive. When you take the absolute value of a positive number, and just think about the x or the y coordinates of this part of the graph, the absolute value of these numbers, absolute value of any positive number would be unchanged. So that is one way you could get the absolute value of, or sketch the graph of an absolute value function, if it happens to have a vertex on the origin, which it could be anywhere. So this is a special case, but it is nice to see that that connection, that the absolute value of a negative number is a positive number, the absolute value of a positive number is unchanged. Now, what we need, though, is without a calculator, we need some practice with writing out the linear transformation equations. All 3 of these are child of this parent. This is the parent function. There's only 10 parents in Algebra 2. This is parent number 3. So from this parent graph, I would like you to practice writing linear transformation equations for number 1. So to get the graph of number 1, there's a point at which I'm going to ask you to pause the video in order to write these out on your own. And for the sake of time, we're going to skip this graph. We're going to focus just on this one. And we're going to take the points from the parent graph, x parent, y parent, the same triplet of points that we've been using the whole time. And go ahead and try to write the linear transformation equations for x child and y child. Put a box around them. Then we'll use these in order to find the 3 points on the child graph. So go ahead and pause the video. Try to complete these 2 equations. Welcome back. Okay, mathematicians call these linear transformation equations. They give us directions on how to transform a parent graph into a child graph. Hopefully, you looked at this and said that the multiply by -2, add 3 process can be inversed or reversed by subtracting 3 and dividing by -2. The inverse of a function is a very important concept in mathematics. Notice that nothing's happening to the y value is 1, 0, 1. but the orange X parent values are going to be transformed according to this equation, which I will put this equation in orange also. Put that back to green. But if you haven't already, transform all three of these X parent values to X child values using the rule X parent value subtract 3 divided by -2. So -1 minus 3 is -4 divided by -2 is 2. 0 minus 3, so that's going to be 1.5. And 1 minus 3 is -2, so that's going to be 1. So when you sketch the graph, you get 2, 1, 1.5, 0, and 1, 1. Okay? And when we go to the next page, it says, remember that from graph number 3, y equals absolute value of x on the previous page. Put the equation in your calculator and graph. What you can do, if you'd like, we did these in class, where the absolute value of x is the parent graph that looks like this. And so that'll be what I have as orange. Now we're going to think about what would happen if you typed this one into your calculator, absolute value of x plus 1. The movie form of this blue equation would be y minus 1 equals the absolute value of x, which means that nothing's happening in the x movie. X child is the same thing as x parent. There's nothing happening there. But the y movie is a little more interesting. Y child is, instead of subtract 1, when you watch that movie backwards, it's plus 1. So what this is going to do is this is going to take the parent graph and shift it up 1. If you type that into your calculator, it will undoubtedly, according to this linear transformation equation for y, it's going to take the parent graph, y parent, it's going to add 1 to all the y coordinates. That's going to shift it up 1. So the calculator confirms that. If we go to the y equals menu, I have another equation up there in y1. If we do math absolute value x, here's the parent graph, I have it in y2, and math absolute value x, close the parentheses or go outside the absolute value of plus 1, you do in fact see the parent graph is shifted up 1. And here it's clear that the pattern is being established and continuing. Now the parent graph is going to go up 2. And the truth is, for these movies that have just one part to them, like subtract 1, you can do those in your head. You don't have to write out the linear transformation equations. You know that if this is up 1, this is going to take the parent graph and go up 2. And to color code this, I want to keep the color coding consistent. I don't know if I can pull this off. I'm going to lock down the orange one so I can change the colors of the purple one. So the parent is in orange. We're going to make this one purple or magenta. The next one will be green. So when you take the parent graph and shift it up 2, the calculator undoubtedly will give you a child graph that is 2 units higher than the parent graph. And you can even go, we'll go to red now. This minus 3 is going to have the effect of taking the parent graph and shifting it down 3. So 1, 2, 3, the calculator will confirm that. So basically what happens when a number is added out the end, there's going to be a shift of the parent graph, shift of the parent, either up or down. On the next page, it's going quickly, there's not a lot to do here. All you're going to have to do is turn this in to show that you took notes. Here we're going to take the parent graph, and this time the parent graph will be red. And we're going to, well, this is just the add 1 movie. So x child would equal x parent. When you watch it backwards, it would be minus 1. So this is going to take the parent graph and go left 1. Let's pick blue for this one. So the labeling is actually a good idea. Y equals x Absolute value of x is the parent graph. So to shift it left 1, just take the whole parent graph, shift it left 1. These should go pretty quickly. Label it with y equals the absolute value of x plus 1. And you might be thinking, well, plus 1, does that mean right 1? No, we're watching the movie backwards and shifting you left 1. Try 7 and 8 on your own. You can pause the video, complete 7 and 8. So, welcome back. I'm doing 7 in magenta. This is going to be left 3. So when we shift this left 3, magenta goes, here's the parent graph, shifted left 3, labeled y equals, it's actually labeled by color. Y equals the absolute value of x plus 3. And then the last one you should have done was the minus 2, which is going to be a shift of 2 to the right. So it's going to be right 2. So parent graph shifted right 2 in green will look like this. The calculator will confirm that. If you don't believe it, then the calculator will enable you to confirm that by just typing in, just checking in the last one. Math absolute value of x, it was x, last one was minus 2. So I'm going to type in x minus 2, press graph, and sure enough, it takes the parent graph and shifts it 2 units to the right. So calculators are great for confirming that. Basically, what happens when you add or subtract on the inside, we'll use parallel construction with what we had in the first one. I mean, on the previous page, we said we shift parent up or down. So here, when there's a number on the inside, adding or subtracting, we're going to shift the parent left or right. So that's a basic idea. They want you to practice this a little bit. So go ahead and take the parent graph and shift it up, down, left, or right on this page. Do all 6 of them on your own. The last 2 have double shifts. So like this one's going to be right 2. And when you put it in movie form, you'll be able to see it. Y plus 3 equals the absolute value of x minus 2. This one down here, number 5, is going to be right 2 and down 3. Watch the movie backwards. Right 2 and down 3. So try all of those on your own. Press pause and then see what the answers turn out to be when you come back. Okay, so this page 3. This page 3 practice should have answers that look like this. We're going left 2 on this one, so the vertex will be at -2, 0. This one is going to be down 4, so the vertex is at 0, -4. It's a good idea to put the language here. Left 2, this is going to be down 4. This one, RT for right 3, we'll put the vertex right here. And up 3 gives us a final answer right there. So notice how quickly these go. These are fast problems. Here we're going to take the parent graph. We're going to go right 2 and down 3. So right 2, down 3 gives us this graph. And I read this one as left 1 and it'll be up 2 because it is consistent. As long as you put the equation in linear transformation form or movie form, more informally, we can see it's going to be left 1. Please write down the words. Be verbal about your math. Left 1 and up 2, because plus means subtract. The inverse of subtraction is addition. So if I move the vertex left 1 and up 2, the child graph will be located right here. On the last page, you have just more practice. So this will be our last run here. Last part of the video. Go ahead and press pause and do these 6 problems on your own, then come back to see how we did. Okay, here it is. Here's the last 2 minutes of the video. I hope you do right 1. This one will end up being up 2 when you put it over there and take the inverse. So right 1 up 2 gives us this. And the verbal on this will be left 4, down 3. So 1, 2, 3, 4, down 1, 2, 3. The vertex is located right here. Number 9 is left 3, up 1. So we go 1, 2, 3, up 1 to get the answer. I think this is just down 5 to get a vertex at 0, -5. This is LT4, left 4, 1, 2, 3, 4. And the last one is going to be right 2, down 4 to get 1, 2, 1, 2, 3, 4. We're done. So bring this in with you, turn it in Monday, and enjoy the rest of your weekend. See you Monday.